Hello, my name's Jolene Rhodes, and in this lesson we're going to talk about MacLaurin Series. I am going to assume that you have talked about Taylor Series prior to this lesson, but we are going to, in this lesson, develop a MacLaurin Series for two functions, and then we're also going to use those MacLaurin Series to find MacLaurin Series for other functions. So we're going to we have two goals for this lesson. Now, before we can get started, a MacLaurin series is actually just a specialized Taylor series. A Taylor series can be centered at any value for x. A MacLaurin series is always centered at 0, which means your function and your series are, the series is centered at 0, which means that if you use just a few terms of your series, it exactly matches the function at 0 and then will be close to your function for values of x around 0. If you use all of the terms of your series, of course the series and the function are actually equal for all values of x where it converges. So to start this conversation, what I want to do is let's start with pretty much the definition of how we get a MacLaurin series. It comes from the Taylor series definition and the Taylor series derivation, but what we're going to do is, in order to write the MacLaurin series, our function is going to be equal to the series n going from 0 to infinity, the nth derivative of your function at 0 divided by n factorial times x to the nth power. If we write out a few of these terms, that means we're going to get the function evaluated at 0. So when n is 0, we get the function evaluated at 0, x to the 0 power, plus then n equal to 1. So this is n equal to 0. When n is equal to 1, we're going to get the first derivative at 0 over 1 factorial, which is just 1, x to the first power, plus, when n is equal to 2, we're going to get the second derivative at 0 over 2 factorial, x to the second power, and so on and so forth for the rest of our values for n. So this is an infinite series. It will continue on forever. The goal usually when we write a MacLaurin series for a function is either to just write the first few terms to use it as an approximation, or to write enough terms that you can see a pattern so that we can write a concise series for our function. Now, example that I want to start with today to do this, I think we're going to use the function f of x equal to cosine of x. And again, this is going to be centered at x equal to 0 because we're going to talk about MacLaurin series. So we're going to put our center at x equal to 0. Now, in order to do this, what we're going to do is we need our function, which is cosine of x. We're going to want several derivatives. So I'm going to do the first derivative of x. Derivative of cosine of x is negative sine of x. Second derivative of x, derivative of negative sine of x, is negative cosine of x. Third derivative is sine of x. Fourth derivative is cosine of x. Notice we've wrapped back around, and let's just do one more here. We'll have the fifth derivative, which is back to negative sine of x. So using sines and cosines, our derivative, starting at the fourth derivative, is exactly the same as our function, and it'll continue in that same pattern. Now, in order to fill into our definition of a MacLaurin series, what we want to do is actually we need all of these derivatives and our functions at what we've chosen to be the center, which is at x equal to 0. So what we really want to do is evaluate these at x equal to 0. So I want f of 0, cosine of 0 is 1, f prime of 0, sine of 0, or negative sine of 0, is 0. Second derivative at 0 is negative 1. Third derivative at 0 is 0. Fourth derivative at 0 is cosine of 0, which is 1. And the fifth derivative at 0 is, again, 0. So what we're going to do is go ahead and evaluate some of our derivatives. Now what we're going to do is say, okay, so let's write out what we have up above. This tells me that cosine of x, so let's go back up to the definition, is equal to f of 0, which is 1, plus f prime of 0, which is 0, over 1 factorial times x to the first power, plus the second derivative, which is negative 1 over 2 factorial x to the second power, plus the third derivative, which is 0, over 3 factorial x to the third power, plus the fourth derivative, which is 1 over 4 factorial x to the fourth power, plus we're going to get the fifth derivative, that's the last one I found, over 5 factorial x to the fifth power, and this would actually continue on, but that's as far as we went. Now with cosine, what I want you to notice is, what do we notice? We notice that all of the odd terms, where x is to the first power, third power, and fifth power, all of our derivatives were 0. So those terms are going to drop out. So what we actually have here is 1 minus 1 over 2 factorial x squared, plus 1 over 4 factorial x to the fourth. And I think if you follow that pattern, you'll notice the next one will be a minus, and we'll continue on in that pattern. Now, if you look at that pattern, let's go ahead and see if we can't write this in series form. So let's use our sigma. We're going to start n at 0, going to infinity. Now, what we want to notice is, or what you should notice here, is all of the terms that we have left are even powers. We really have an x to the 0 power, x squared, x to the fourth, and so on. And what we actually have is our coefficients are just the same as our power factorial. So what I have here is, in order to get an only even powers, what I want is an exponent of, say, 2 times n. When n is 0, that will give me 0. When n is 1, I get 2. N is 2, I get 4, and so on. So we'll get just even exponents that way. And what we notice again is what our factorials in the denominator, or in our coefficients, are also are the same as our exponents. And one last thing, what we need to notice is what these terms alternate in sign. So what we need is, this is an alternating series, so what we're going to do is go ahead and we're going to add an alternating piece in here. What I'm going to do is do negative 1 to the nth power. That way when n starts at 0, that's a positive 1. When n is 1, that's a negative, and so on and so forth. And if you wrote out a few of those terms, you could see that it actually agrees with the series that we had above it. And so that is our series for cosine of x. So what we actually have now is the MacLaurin series for cosine of x, which is going to be the series n going from 0 to infinity, negative 1 to the n, x to the 2n power, all divided by 2n factorial. Now, when you have a MacLaurin series, once you get one MacLaurin series, you can actually get a whole family of MacLaurin series. We are allowed to use the MacLaurin series that we know, and to get other MacLaurin series by 3 methods. One, we can use substitution. And what I mean by that is we could, for example, find the series for cosine of 3x. If you know the series for cosine of x, you can find the series for cosine of 3x, because what we're going to do is simply look at the series that we have above, and we've replaced that x by 3x. We're going to, if we do that on one side of our equal sign, we're going to do that on the other. So what I'll get is the series n going from 0 to infinity, negative 1 to the n. Where the x is, we're going to put 3x. So I'll get 3x to the 2n power over 2n factorial. Now you may want to write it that way, or you may want to separate those pieces to the exponent. I'll get a negative 1 to the n, a 3 to the 2n, an x to the 2n, and a 2n factorial in our denominator. Either way is correct. So we can find a series by substitution. We could find another one. We could do, say, cosine of x squared, if we want that series. Again, what we're going to do is replace x by x squared in our series that we found earlier. So we'll get negative 1 to the n. We're going to get x squared to the 2n over 2n factorial. Or, doing some simplifying, that's going to be the series n going from 0 to infinity, negative 1 to the n, x to the, when we raise a power to a power, we're going to multiply those two. So 2 times 2n gets us the 4n power. And again, this is just over 2n factorial. So that's one way to get a new series from a known series. We can use substitution. The second way to get a new MacLaurin series from a known MacLaurin series is you can take a derivative. And the third way is by integration. So we could integrate both sides. Now I'm going to use that third thought here because we know that if we integrate cosine of x, what we get is sine of x plus c. We're not going to worry about our constants in this case, but what we are going to do then is the integral of cosine of x is sine of x. So if I look at this and I wanted a series for sine of x, so if we want a MacLaurin series for sine of x, then this is, sine of x is the integral of cosine of x. But we know from earlier that the series for cosine of x is the series from 0 to infinity of negative 1 to the n, x to the 2n over 2n factorial. Now we are taking this integral with respect to x. So when we integrate with respect to x, all of the non-x terms are treated as constants. So we are actually, an integral sign, if you remember, an integral sign is actually also a summation. So we actually have a summation of a summation. You can do those in whatever order. So really what I'm going to do is pull my summation sign from my series out front. I'm going to have a series from n going from 0 to infinity. Negative 1 to the n is a constant. 2n factorial is a constant. And so what we're really just integrating is just the x to the 2n part. That's the part that has the x. Well, okay, I can integrate x to the 2n. That's just x to a power. And if we're going to integrate x to a power, all we do is add 1 to our exponent. So we're going to add 1 to our exponent and divide by that exponent. And so we're going to get x to the 2n plus 1 divided by 2n plus 1. Now if we look at this and just look at a little bit, what that really is this is the series from n going from 0 to infinity. I got a negative 1 to the n. We have an x to the 2n plus 1. Let's look at the denominator for a minute. What I have is 2n plus 1 times 2n factorial. Well, if I look at 2n factorial, that takes me all the way from 2n all the way down to 1 in factorials. The 2n plus 1 is the term actually one bigger than that. So if we put those together, that is actually the same as 2n plus 1 factorial. And now through integration, what we actually have is a series for sine of x. So the series for sine of x is negative 1 to the n, x to the 2n plus 1 all over 2n plus 1 factorial. Now one last thought about sine and cosine, about these two, is that if you notice the series for cosine had all even terms. What you should have learned in trig is that cosine is an even function. It's symmetric about the y-axis, and so it's an even function. And sine is an odd function. If we look at this and we look at our exponents on sine, then all of 2n plus 1 will always be an odd number. It's going to be 1, 3, 5, and so on. And all of the even terms went away. So sine ends up with a polynomial of all odd exponents, and cosine ended up with a polynomial with all even exponents, which is what we should expect because they are even and odd functions, as we saw in trig. Now let me show you one more thing that we can do with MacLaurin series, some of the MacLaurin series that we found. And we just found the MacLaurin series for sine of x. So let's go ahead and use that for a minute. And let's look at the series for, say, sine of x cubed. And let's find a MacLaurin series for the sine of x cubed. If we do that, then what we're going to do, again, is we're going to take the series we just found. So the series n going from 0 to infinity, negative 1 to the n. We're going to replace x by x cubed in that series to the 2n plus 1 over 2n plus 1 factorial. Or this is now the series n going from 0 to infinity, negative 1 to the n, x to the, if we multiply our exponents, we're going to get 6n plus 3. This is divided by 2n plus 1 factorial. Now, one of the things that when you've done the integration chapter is sine of x cubed. That integral is not an elementary integral. It's not the one that we actually learn how to integrate. But we would like to know how to integrate it. And so one of the things that we can do, though, we can't actually integrate sine of x cubed with any of our basic integration techniques that we learn in Calc 2. But what we can do now is we can always integrate the MacLaurin series, because remember, the MacLaurin series is just basically a polynomial. So what I can do is, if I want to know what the integral of sine of x cubed is, then what I'm going to do is integrate that series, n going from 0 to infinity, negative 1 to the n, x to the 6n plus 3 over 2n plus 1 factorial. And again, we're going to leave the series part, everything without an x. Let's just write all of that down. And the only thing that we're integrating is x to the 6n plus 3. And again, in order to integrate that, what we're going to do is what? We're going to add 1 to our exponent and divide by our exponent. So 6n plus 3 plus 1 is going to give me x to the 6n plus 4. So I have a new exponent of 6n plus 4. We're then going to divide by 6n plus 4. And now what I actually have is a series representation for that integral. So we could use the series to approximate the values of the integral. It can give us an approximation method. We could use the first couple terms of the series to approximate that integral, keeping in mind that it is centered at 0. So we're going to have the best approximations as long as we stay with x values near 0 if we're only using certain terms. One last thought about series is that I've worked from the function to the series, but you could do this backwards. What we could do is say, if I have a series, maybe I'm given a series where the series is n going from 0 to infinity, negative 1 to the n, pi over 3 to the 2n over 2n factorial, and I want to know what is the sum of that series. So my question is, what is the sum of the series? Well, if we recognize that series, then I do recognize that series. That was my series for cosine of x, where x has been replaced with pi over 3. So the sum of this series is actually then just going to be cosine of pi over 3, because the series itself looks like the series for cosine, where the x is, we've replaced it with pi over 3. What we now just want to do is say, what's the cosine of pi over 3? And the cosine of pi over 3 is 1/2. So the sum of this series is actually 1/2. And so we can do these problems in reverse too. So if you know what you're given the series, you can sometimes find its sum. If you're given the function, we hopefully can find the series either from the definition or from series that we have derived or we found in another earlier. And that concludes this lesson. Thank you.